Virtual reality and augmented reality are two advanced technologies that alter our perception of the world around us, but they do so in fundamentally different ways. Virtual reality, or VR, is a technology that creates a completely immersive digital environment that replaces the user's real-world surroundings. This is typically achieved through a VR headset, which covers the eyes and often includes headphones for sound. The headset tracks the user's head movements, and the computer adjusts the image on screen inside the headset to match, creating the illusion of being inside a virtual world. Meanwhile, augmented reality, or AR, overlays digital information onto the real world. Unlike VR, it doesn't create a completely immersive environment. Instead, it enhances the user's perception of reality by adding computer-generated information such as images, sounds, and text to their view of the real world. AR can be experienced through AR glasses or handheld devices such as smartphones or tablets. The device's cameras capture the real world, then displays it on screen, with digital additions overlaid on top. One of the main features for VR and AR devices is 3D position and rotation tracking. The physics behind 3D head tracking in VR and AR headsets involves a combination of hardware and software technologies that work together to track the movement and orientation of a user's head in real time. This tracking allows the system to adjust the images seen by the user to create a realistic and immersive experience. The key components to do this consist of gyroscopes, accelerometers, and magnetometers, which are all combined into an inertial measurement unit, also known as an IMU. Each of these sensing elements must also sense the measured properties in three axes, X, Y, and Z. Combining these signals facilitates error correction and yields accurate measurements to track head position and movement. Now, VR and AR devices can either be in 3 degrees of freedom, which means just the rotation in the pitch, roll, and yaw, or 6 degrees of freedom, which has the pitch, roll, yaw, and can measure movement in the X, Y, and Z coordinates. For the mathematical model of an IMU that we're going to cover, it's going to be 6 degrees of freedom. The gyroscope model that's used is omega equals omega hat plus b sub g plus n sub g, where omega is the measured angular velocity from the gyro. Omega hat is the latent ideal angular velocity we wish to recover. B sub g is the gyro bias, which changes with time and other factors like temperature. And n sub g is the white Gaussian gyro noise. The gyro bias is modeled as b sub g hat equals b sub g of t, distributed as a normal distribution with a mean of 0 and a variance of q sub g, where q sub g is the covariance matrix which models gyro noise. Now, the accelerometer model shows that A equals R transpose times the quantity A hat minus G plus B sub A plus N sub A, where A is the measured acceleration, A hat is the latent ideal acceleration that we want to recover, R is the orientation of the sensor in the world frame, G is the acceleration due to gravity in the world frame, B sub A is the acceleration bias, which changes with time and other factors like temperature, and N sub A, which is the white Gaussian acceleration noise. The acceleration bias is modeled as B sub A hat equals B sub A of t, distributed as normal distribution with a mean of 0 and a variance of Q sub A, where Q sub A is the covariance matrix which models acceleration noise. Here, the orientation of the sensor is either known from external sources such as a motion capture system, a camera, or estimated by sensor fusion. Now, looking at the mathematical formulation, the values gathered from these functions get put into what's called a Kalman filter. This filter starts by taking the input as the current state to predict the future state. A state in a Kalman filter is the vector which you'd like to estimate. In our case, we'd like to estimate the attitude of the IMU. Along with estimating the attitude, we'd like to also estimate the bias of the gyro so that we can get a more accurate estimation. Let's denote our state at time t by x sub t, which is given by x sub t equals this column vector with the entries phi sub t, theta sub t, psi sub t, and b sub gt. Here, b sub gt belongs to the set of real numbers in 3 dimensions by 1 dimension, which denotes the gyro bias in 3D. Following are the steps for the attitude estimation using the Kalman filter. The first step is to obtain gyro and accelerometer measurements from the sensor, where I omega sub t and I a sub t denote the gyro and accelerometer measurements respectively. Step 2 is to process updates using the gyro measurements, which is just prediction. First, we want to compute the predicted next state using the system dynamics. We have to note that the KF each state is characterized by its mean and covariance matrix. And here's the formula to find that. Here, where mu sub t and sigma sub t denote the mean and covariance of the state at time t and mu hat sub t plus 1. Sigma hat sub t plus 1 denotes the estimated mean and covariance of the state at time t plus 1. Q sub t plus 1 denotes the noise matrix modeling how noisy the system dynamics model is. Here, at A sub t plus 1 denotes the process dynamics or system model, which mathematically models how the state changes from t to t plus 1, and is given here. Here, delta t is a time elapsed between two samples at t and t plus 1. If no correction is given, this prediction would drift due to the error in process model. The process model, in our case, models a constant attitude within the small time instant, but the bias integrates over the small time delta t. Also, u sub t plus 1 represents the input process vector and is given by u sub t plus 1 equals a column vector with the entries phi dot, theta dot, and psi dot. Where this column vector with the entries phi dot, theta dot, and psi dot equals r inverse times omega sub t, where r equals this matrix here. Now, b sub t plus 1 denotes the mapping of the input vector to the state vector and is given by b sub t plus 1, which equals this matrix here. Here, the bias is assumed to be not dependent on the attitude, which might not be true in real life. The next step is step 3, measurements updating using the accelerometer measurements, specifically dealing with fusion or correction. In this step, we compute the attitude using the accelerometer measurements and use it to obtain the corrected state, which is the state that is in combination of both the process and measurement steps. This step entails the sensor's fusion. These are the functions how we do this. K sub t plus 1 equals sigma hat sub t plus 1 times c transpose times the quantity sigma t hat sub t plus 1 times c transpose plus r, all raised to the power of negative 1. Mu sub t plus 1 equals mu hat sub t plus 1 plus k sub t plus 1 times the quantity z sub t plus 1 minus c times mu hat sub t plus 1. Sigma sub t plus 1 equals sigma hat sub t plus 1 minus k sub t plus 1 times c sigma hat sub t plus 1. Here, z sub t plus 1 denotes the observable state by the sensor. This could be a subset of the full state, as in our case. Now, the accelerometer is used to obtain the angles as follows. Phi equals the inverse tangent of a sub y divided by the square root of a sub x squared plus a sub z squared. Theta equals the inverse tangent of a sub x divided by the square root of a sub y squared plus a sub z squared. Here, c denotes the mapping from the observed state to the full state, and is given by c equaling this matrix here. Note that in our case, we don't use the value of psi from the accelerometer readings, as it generally is inaccurate. In a real robotic system, the value of psi is obtained from a camera or a compass. The rows of all zeros in the C indicate unobservable values in the state vector x. Now we want to repeat steps 1 and 2 for every instant of time, and step 3 whenever a measurement update from the accelerometer is available. Now the measurement update is generally run about a factor or 2 of magnitude slower than the process update for keeping computation complexity low. But in conclusion, this is how the physics of motion tracking is done in VR and AR devices.